Hello, and thank you for taking the time to listen to my talk. My name is Daniel Rico, and I am a graduate research assistant at the University of Nebraska-Lincoln in the School of Computing, formerly the Department of Computer Science and Engineering, and a member of the Nebraska Intelligent Mobile Unmanned Systems, or NIMBUS, and the Hydroinformatics and Integrated Hydroclimate, or HIH, laboratories. I'm advised by Dr. Carrick Detweiler of NIMBUS and Dr. Muniz Ariola of the HIH laboratory. The title of this talk and our contributed proceedings paper is Trajectory Selection for Power over Tether Atmospheric Sensing UAS. We previously developed the Tethered Aircraft Unmanned System, or TOS, which is a novel power over tether UAS configured for long-term, high-throughput atmospheric monitoring via an array of atmospheric temperature sensors embedded along the power tether. The system uses electrical power transmission rather than onboard lithium polymer batteries to dramatically increase the UAS's flight time and therefore acquisition time of high-resolution spatial temporal data. We shown in our paper published in 2020 to the American Society of Agricultural and Biological Engineers, or ASABE, the development of the system in static field operations. Building upon our previous work, we present here operational performance validation of the TOS, a power over tether UAS and temperature sensor models, and the implementation of trajectories on the TOS model to assess theoretical performance of the physical system. The main contributions of the work presented here are as follows: field experiments and results demonstrating validation of operational performance of this platform to sense temperature fluctuations within a 15-meter above ground level range, development of a model that represents the physics governing power over tether UASs in flight, design and implementation of power over tether trajectories for the model to evaluate theoretical performance via factors and a bounded volume of a simulated atmosphere. We took the TOS to a local outdoor research facility, which had a 10-meter meteorological tower with well-maintained atmospheric temperature sensors at 2 meters and 10 meters above ground level. The TOS was deployed for approximately 1 hour before dawn to maintain a quasi-static position alongside the tower, as seen in the image to the left. The atmospheric temperature data acquired between the two systems is shown on the right. We were specifically interested in validating sensors at comparable altitude, sensor 3 and sensor 1 of the TOS, and the tower sensors at 10 meters and 2 meters respectively. We conducted an intercomparison between the sensors and calculated statistics, including the RMS error between them. As we can see from the table, sensor 1 and tower sensor at 2-meter AGL has an error of 0.143 degrees C, and sensor 3 and tower sensor at 10-meter AGL has an error of 0.091 degrees C. With such a relatively small error, we considered our system valid in the field when operating in a quasi-static manner. Since our system has a power sensing tether, it is physically bounded. In order to model and simulate the actual system, we need to first derive the Euclidean spatial bounding. Here's an abstract representation of our system. The arc that is formed is formally known as a catenary, which is defined as a hyperbolic cosine function. In our range of operation, we can approximate this catenary behavior with a simple quadratic parabola. The TOS has 15.375 meters of power sensing tether. Therefore, the length of the arc can be expressed as such, where the function s is parabolic. We then evaluate the integral, solving for the upper bound b, which leaves us with a spatial bound in the x and y dimensions of 3.814 meters. Evaluating the parabolic function with 3.814 gives us the z bound of 14.543 meters. Thus, the TOS was bounded in Euclidean space. Since our function is parabolic, we can invoke an equation for finding the theoretical maximum volume of a paraboloid. We then evaluate from 0 to h. And find 332.22 cubic meters is the approximated theoretical maximum volume traversable by the system. Once the system was bounded, we considered 9 factors to evaluate trajectory simulations of the system against, relating to spatial and temporal components. First is the flight duration in seconds of a single trajectory. Volume encompassed in cubic meters provided by invoking a 3-dimensional convex hull algorithm, seen in cyan here. Coverage of discrete points in space as a percentage where the discrete points are a field of static points separated by 1 meter throughout the simulation volume. Successful sampling of these discrete points was considered distances of less than or equal to 0.5 meters to the point centroid from the sensors of the TOS. Coverage of discrete points in space after 30 seconds of traversal, which makes this factor relating to both space and time. Similarly, coverage of discrete points in space with 30 seconds of traversal remaining. Dynamic temperature field reconstruction error, which is the RMS error between the TOS simulation's ability to reconstruct the dynamic input temperature field. Detection time in seconds, which is the time it takes for any given trajectory to determine it is sampling a changing or dynamic temperature field. This factor helps determine which trajectories detect temperature field changes quickest. Energy consumption in kilojoules, and accumulated data in packets. Now that we have quantified the spatial bounds of the toss and developed a set of factors to evaluate toss trajectories against, we need to develop the model. We leveraged and modified the Freya simulator, which has a high-fidelity 6 degrees of freedom quadcopter UAS model developed in-house by another member of the Nimbus laboratory. We incorporated 30 cylindrical links with 15 universal joint components in MATLAB Simulink, where we modified the joint stiffness and damping properties to emulate the observed behavior of the power sensing tether of the toss. Now that we have the model of the toss, we need to model and incorporate the temperature sensors. Temperature sensors are designed to be linear time invariant systems. They can be expressed as an ordinary first-order differential equation like this. This means the sensor's time to convergence is considered fixed, or said another way, is the time it takes the sensor to fully respond to a change in 5 degrees of temperature should be the same for 50 degrees of temperature and so on. The behavior, or rather response time, is independent of the magnitude of difference. Each temperature sensor has a unique time constant tau, which is the time it takes for the sensor to reach 63.2% of the full step response. This needs to be known before one can actually model the sensor. In order to find this value, we ran a step response experiment on the sensors between a known freezer value and a known room temperature value, and empirically derived it from the post-processing of the data shown here. Now that the models and the means to evaluate their simulation performance have been completed, we needed to select and calculate which trajectories to run. After reading the literature, we decided on the following set. Creeping line or lawnmower, which is traditionally used for full spatial coverage traversals, and it is accomplished by invoking an exhaustive walk. Archimedean spiral, which provides a prolonged but high spatial temporal sampling at a constant lateral step. Pentagram, a quick but low spatial temporal sampling inspired by approximate cellular decomposition trajectories. And flower, inspired by sector search patterns and magnetic particle imaging techniques, which provides a spatial emphasis that translates across the volume. After incorporating the toss and temperature sensor models, we drove the simulations with each of the trajectories' respective mathematics, which can be seen here. These are top-down two-dimensional perspectives on the simulations, but data is being generated in 3 physical dimensions through time. The cyan shape being generated is a byproduct of the convex hull algorithm being invoked. The red line is the trajectory of the UAS. The blue lines are the true Boolean outcomes of the sensor distance exposure to the 1 meter grid point centroids. The multicolored dots are the sensor's physical position at time steps throughout the simulation. The spiral and flower trajectories are written as continuous functions, while the creeping line and pentagram are decomposed into piecewise continuous lines. To be clear, the physical positions of each of the sensors and their response to a given temperature field they are exposed to is being simulated. Here we can see the sensor array spatial and sampling information being represented from a flower trajectory moving through a static temperature field. And here is an animation derived from the simulation. The temperature field is static and not well representative of Earth's atmosphere, but was used as a step towards incorporating dynamic temperature fields. Here we see the pentagram trajectory for the toss. Let's assume a dynamic temperature field represented by a cold front was tracking east through the simulation volume. We would like to investigate what trajectory should a power sensing tethered US fly to quickly and accurately capture or reconstruct the input field best. Here we see the pentagram trajectory in sensor 4's response and reconstruction error being simultaneously plotted. It should be noted in the figure to the left that the power sensing tether's variable slack due to a fixed system altitude is causing a degraded sensor trajectory, particularly closer to the ground station, where slack is most disruptive. After running all of the trajectory simulations, we tabulated the results with respect to the 9 factors of evaluation previously mentioned. As a form of control, we also simulated untethered UAS systems denoted by the -U with a single temperature sensor on board to compare against. There are 6 major takeaways from our post-simulation analysis. First, Tethered system simulations outperformed the untethered in most categories. Specifically, they sampled volumes 34.49 times greater and generated a percent coverage 2.96 times larger, and accumulated 4 times as much data for the same duration of flight. Untethered systems outperform tethered systems in energy, which is to be expected because power tethering is inherently a relatively inefficient configuration. These outcomes are to be expected, and it should be noted that it is not fair comparing bounded untethered systems, but it is useful as a control comparison to provide insight into possible expectations. Second, mower trajectory, both tethered and untethered, showed the most agreement between coverage in the first and coverage in the last 30 seconds. This indicates that the mower trajectory is most spatio-temporally uniform. Third, the tethered spiral trajectory should entirely encompass a traversable volume of 330 cubic meters, but only reported a maximum of 291 cubic meters. We suspect the 11.71% difference is due to the rigid construction of the 3D convex hull and the catenary equation parabolic approximation. Fourth, we expected tethered systems to have significantly less reconstruction error when compared against untethered systems, but we see marginal differences. This is due to our dynamic field construction being uniform in the vertical dimension when there should be a gradient. If this was implemented with the gradient, untethered systems would perform much worse because they are not traversing in the vertical, whereas the tethered system have sensors throughout the vertical column. Fifth, the tethered star trajectory is the quickest and therefore most energy efficient for tethered, and had the smallest temperature reconstruction error at 1.169 degrees C. Sixth, when analyzing the ratio between percent coverage and duration, the tethered mower and star trajectories had the best ratios at 36.7 and 34.7% respectively, suggesting these two trajectories are most spatio-temporally efficient. The worst performer was the untethered flower trajectory at 7.2%. The flower trajectory is circular and slowly translates, thus revisits portions of the volume, making it inherently less spatio-temporally efficient. Finally, from our post-simulation analysis, we would recommend the tethered spiral or flower trajectories if you wanted to maximize volume, coverage, and accumulated data, or the tethered mower star trajectories if you wanted to minimize duration and energy consumption. In conclusion, we conducted a 1-hour quasi-static field experiment to validate the toss against a ground truth tower installation and found minimal sensing error and against the tower sensors. Then we developed a model of the temperature sensors and the toss that represents the physics that governs power tethered UAS along with factors for evaluation. We wrote a set of trajectories for the models to run in simulation through dynamic temperature fields so we could evaluate toss theoretical performance. After analysis, we discovered that the tethered star trajectory minimized key performance factors related to reconstruction error, duration, and energy consumption. With respect to our future work, we would like to validate simulation outcomes on the physical system in the field, close the loop and provide controller feedback for autonomous operation, and develop a network of NTOS nodes to work on collaborative sampling tasks. We'd like to acknowledge and thank our sources of funding, the National Science Foundation, National Aeronautics and Space Administration, the United States Department of Agriculture, and the Daugherty Water for Food Institute Student Support Program. We would also like to thank the University of Nebraska-Lincoln, the Nimbus and HIH Laboratory, and the IEEE IROS 2021 conference for the opportunity to share our work. Thank you all for your attention and interest. Please feel free to reach out to me via email if you have any questions or comments.